You ever look at a complex piece of tech and just wonder, how on earth do engineers deal with the math behind that? Well, today we're going to pull back the curtain on one of their biggest secret weapons. It's a tool that takes some of the gnarliest problems in calculus and, get this, turns them into basic algebra. Yeah, you heard that right. Let's jump in and see how this magic trick actually works. So let's meet the villain of our story. This is a higher order electrical circuit. When you've got multiple energy storing parts, like inductors and capacitors all tangled up, figuring out what it's doing is not easy. This is the kind of thing that gives engineering students nightmares, for sure. And yeah, it looks complicated because, well, it is. To describe what's happening here with math, you end up with this tangled web of what are called differential equations. And trying to solve this thing directly, oh man, it's a huge pain. It's just clumsy and totally impractical. It's basically a mathematical dead end. But hey, don't sweat it. We've got a roadmap to get us through this whole thing. We're going to start with that nightmare problem, then ask a really smart question that changes everything. We'll see how to literally turn calculus into algebra, learn how to solve problems in this new S domain, and then zoom out to see why this is such a big deal. Okay, so let's get right into it. Section 1, the engineer's nightmare. The big question is, when you have a circuit like this, with a bunch of components you can't just simplify away, how in the world do you solve it? So here's the real problem. The normal tools that engineers use for simpler circuits, they just don't work here. If you try to use standard methods like, say, node or mesh analysis, you don't get a nice, simple answer. Nope, you get those ugly, high-order differential equations we just saw. And like I said, trying to solve those directly is just not how you want to be spending your day. So when you're staring at a problem this messy, you know there just has to be a better way, right? Engineers and mathematicians, faced with this kind of wall, they started looking for a shortcut, a more elegant way to get to the answer. And that search led them to this absolute game-changing question. What if we didn't have to fight with this problem on its own terms? What if we could just transform it into something easier? Could we somehow turn that whole mess of differential equations into a simple set of algebraic ones? And the answer, you've probably guessed, is a resounding yes. The tool that makes this happen is the hero of our story today, the Laplace Transform. The best way to think about it is as a kind of mathematical translator. It speaks both languages, calculus and algebra. Okay, now here's the formal definition. And I know, that integral looks pretty scary. But here's the good news. You don't really have to worry about solving it. What's important is what it does. It takes a function that depends on time, our f of t, and it translates it into a new function, f of s, in a completely different world called the S domain. Just think of s as being related to frequency. We're shifting our whole viewpoint from when things happen to how often they happen. And you might be asking, okay, but does this work on everything? And for an engineer, the answer is pretty much yes. As this quote says, basically any function or signal that you'd actually care about in the real world, you can use the Laplace transform on it. It's an incredibly powerful and versatile tool. And this is it. This is the aha moment. This is the heart of the whole thing. The really difficult operations from calculus like differentiation and integration, in the S domain, they become ridiculously simple. Differentiation just becomes multiplying by S. Integration becomes dividing by S. I'm not kidding. The hardest part of the problem just vanished and was replaced by middle school math. It's an absolute game changer. And look at what this does to our circuit components. It's amazing. The resistor, well, it stays the same. But the inductor, with its differential equation, poof, it's just SL. The capacitor, now it's just 1 over SC. All of our circuit parts are now described with simple algebra. We call these their impedances, and they make our lives so much easier. So that's the theory. But how do we actually use this thing to solve a problem? Well, it's not just some abstract idea. It's a very practical, step-by-step method. And here are the steps. It's this beautiful 3-step dance. First, you take your complicated circuit from the time domain and you transform it into the much friendlier S domain. Second, you solve it. But now, solving just means using basic algebra. It's a piece of cake. Finally, once you have your answer in the S domain, you do an inverse transform to bring it back to the real world, the time domain, and that gives you the actual answer you were looking for all along. So what's the payoff? Remember that horrible mess of equations from the very beginning? Well, after you do the 3-step transform, solve, inverse dance, the final answer for the voltage in that circuit looks like this. A clean, beautiful expression. This tells you exactly what the voltage is doing at any point in time. And we got here without ever having to solve those nasty differential equations directly. Pretty cool, right? But this is so much more than just a clever trick for circuits. The Laplace transform is a genuine superpower. It completely changes how engineers think about and design pretty much any complex system you can imagine. One of the most powerful ideas that comes out of this is something called the transfer function. It's simple, really. You just take the Laplace transform of the system's output and divide it by the Laplace transform of the input. What you get, this h of s, is like the system's unique fingerprint. It's its DNA. It tells you everything about the core behavior of that system. So why should you care about that? Because if you know a system's transfer function, you can predict how it will respond to any input you throw at it. This is the absolute foundation of modern control theory. It's how your car's cruise control knows how to handle a hill. It's how noise-canceling headphones work. It's how we design everything from audio filters to rocket guidance systems. This is the key that unlocks our ability to build stable, predictable technology. Ultimately, the Laplace transform teaches us a powerful lesson. Sometimes, the best way to solve a really hard problem isn't to just charge at it head-on. It's to step back and find a different way to look at it, to find the right transformation. Which leaves you with a really cool thought. What other impossible problems out there are just waiting for the right shift in perspective to become simple